So, welcome to lecture series on matrix analysis with applications. So, today we will discuss about spatial matrices. Okay. What spatial matrices are and how we can find out eigenvalues of spatial matrices, what are the important characteristic properties they are having. So, first matrix is symmetric matrix. So, a square matrix A of order n is said to be symmetric if A is equal to A transpose. Transpose means you interchange rows and columns, and if interchanging rows and columns the matrix will remain unchanged, that means matrix is symmetric, then we say the matrix is symmetric. For example, you see this matrix, if you interchange rows and columns, okay, so this matrix is you can find that A transpose is equal to A. If you see this matrix, so these two elements are not same, that is A is not equal to A transpose here, so this matrix is not symmetric. So, we can always construct a symmetric matrix like this. Suppose you are having a matrix, you can arbitrarily put any diagonal elements. If it is 4 here, 4 here, 5 here, 5 here, say 7 here, minus 7 here, minus 7 here. So, if you find its transpose, so it is always 1, 4, 5. You interchange these rows and columns, 4 to minus 7, 5 minus 7, 3. So, you can easily see that A transpose is equal to A. So, we can say that A is a symmetric matrix. Okay. Now, what are properties of symmetric matrices? Any real symmetric matrix, real means all entries are real, okay, has only real eigenvalues. Suppose matrix is symmetric, that is A is equals to A transpose and matrix of order n cross n. Now, we know that any matrix A, matrix may have complex roots also, I mean complex eigenvalues also, but if it is a real symmetric matrix, it always have only real eigenvalues. How we can prove it? So, the proof is simple, you can see here. Let us suppose Ax equal to lambda x and x is not equal to 0. Okay. So, that means A has an eigenvalue lambda and the corresponding eigenvector is x. Now, you take bar both the sides, bar means conjugate. How you can find the conjugate of a matrix? You simply find conjugate of each element of the matrix, that will be A bar and is equal to lambda bar x bar. You can take conjugate both the sides. Now, you take transpose both the sides. So, it is conjugate whole transpose is equal to lambda bar x bar whole transpose. So, this implies x bar transpose A bar transpose is equal to lambda bar x bar transpose. Lambda bar is a scalar, so its transpose will be itself. Now, since A is a real matrix, so A bar will be itself. So, we can write is equal to x bar transpose A is equals to lambda bar x bar transpose, okay, A transpose, and A transpose is A because A is symmetric. So, this implies x bar transpose A is equals to lambda bar x bar transpose. Now, you multiply both sides by post multiplied both sides by vector x. So, this is x bar transpose A x is equals to lambda bar x bar transpose x. Now, this A x is lambda x, this we have already taken. So, it is lambda x, lambda bar transpose lambda x, lambda bar x bar transpose x. So, this implies lambda can be taken out. So, lambda minus lambda bar times x bar transpose x is equal to 0. Now, if x is this vector x1, x2 up to xn, then x bar transpose will be x1 bar, x2 bar and so on up to xn bar. And what will be x bar transpose x? This will be mod x1 square, because x1 bar into x1, which is mod x1 square plus mod x2 square and so on up to mod xn square, and it is not equal to 0 since x is not equal to 0. It will be 0 only when all xi's are 0, and all xi equal to 0 means x equal to 0, but x is not equal to 0. So, that means this is not equal to 0. Now, this is not equal to 0, this means lambda minus lambda bar is equal to 0 because product of these two is equal to 0. So, this implies lambda equal to lambda bar, and if number and is equal to its conjugate, that means lambda is purely real, lambda is real. So, we have taken an arbitrary lambda for an symmetric matrix A and we have shown that lambda is real, that means all eigenvalues are real for a symmetric matrix. So, this is the first property of symmetric matrix, that eigenvalues are always real. The next property is it is always diagonalizable, that means if you have any real symmetric matrix A, then you can always find an invertible matrix P such that AP is equals to PD if A is symmetric, always. Next is it has orthogonal eigenvectors. Using the second property, is it easy to show? You see, because we know that every symmetric matrix is always, every real symmetric matrix is always diagonalizable, that means if A is a real symmetric matrix, then A is diagonalizable, always diagonalizable. Okay. Now, that means this implies there exists an invertible matrix P, invertible matrix P such that A P equal to P D or A is equals to P D P inverse, where these are the diagonal values of, eigenvalues of A, which are all real. This we have already seen because A is symmetric. Okay. Now you can take transpose both the sides because A is symmetric. So, it is P D P inverse whole transpose. This is equal to A transpose is equal to A because A is real symmetric matrix, and it is P inverse transpose D transpose P transpose. It is P transpose whole inverse, D transpose is D itself because it is a diagonal matrix, and it is P transpose, and A is nothing but P D P inverse. So, it is P D P inverse is equal to this. So, from here we can conclude that one of the conclusion from here is P inverse is equals to P transpose, or P transpose P is equal to identity. Okay. Now what is P? P is simply a matrix of eigenvectors. We have already seen the construction of such P's. So what is P? P is simply x1, x2 up to xn. These are eigenvector corresponding to lambda 1, lambda 2 up to lambda n. So, what is P transpose P? It will be x1 in this row, x2 in this row, up to xn in this row, and this is x1 in this column and so on up to xn in this column. Okay. So what it is equal to? You see this row, this column, when you multiply this row, this column, this is nothing but norm of x1 square. Okay. When you multiply this row with this column, this will be nothing but x1 transpose x2, and similarly it is x1 transpose xn, xn transpose x1, xn transpose x2, and so on up to xn norm square. And this is equal to identity, this we have shown. This equal to identity means all norms of all the vectors are is equal to 1 and all other entries are 0. That means eigenvectors are orthogonal, in fact orthonormal. Okay. It simply means that xi transpose xj is equal to 0 if I not equal to j, and it is 1 when I equal to j. So, that means this set x1, x2 up to xn, this set is orthonormal. So, hence we can say that they has orthogonal eigenvectors, or If it is orthonormal, then it is orthogonal also. Okay. So, these are the properties of similar matrices. Now, next is skew symmetric matrix. A square matrix A of order n is said to be skew symmetric matrix if A transpose is equal to minus A. Okay. Suppose you see this matrix, if you take A transpose of this matrix, it is simply equal to minus of A. So, hence this matrix is skew symmetric. However, this matrix is not skew symmetric because when you take minus A transpose, it is not equal to minus of A for this problem, minus of B. Okay. So, what are properties of skew symmetric matrix? Let us see. Now, for skew symmetric, A transpose is equals to minus A. A is n cross n skew symmetric. Okay. Now, if A is skew symmetric, the first property is that if n is odd, order of the matrix is odd, then determinant of A is 0, if A is skew symmetric. Proof is simple, you can see here A transpose is equal to minus A, this implies determinant of A transpose is equal to determinant of minus A. This implies determinant of A transpose is same as determinant of A, and determinant of minus 1 minus times A is minus 1 raised to power n into determinant of A. So, if n is odd, then minus 1 raised to power n will be minus 1. So, determinant of A will be minus determinant of A, and this implies determinant of A is equal to 0. So, the first property is that a skew symmetric matrix of odd order has 0 determinant, or any skew symmetric matrix of order odd order is always singular, the first property. Now, second property is skew symmetric matrix, all the eigenvalues of the skew symmetric matrix are either 0 or purely imaginary. How we can prove this? So, let us see the proof. Now, A transpose is equals to minus A is n cross n skew symmetric matrix. So, Ax equal to lambda x, take Ax equal to lambda x, x is not equal to 0. Again take bar both the sides, take transpose both the sides. So, taking transpose we get this expression. Okay. Now, since A is a we are taking A as a real skew symmetric matrix for this case. So, x bar transpose it is A transpose lambda bar x bar transpose. This implies x bar transpose A transpose is minus A. So, it is minus of A is equals to lambda bar x bar transpose, post multiply both side by vector x. This implies Ax equal to lambda x, you can substitute here, and this implies lambda bar plus lambda times x bar transpose x is equal to 0, and x bar transpose x is not equal to 0, this we have already shown in the last proof. So, as x bar transpose x is not equal to 0. So, this implies lambda bar plus lambda equal to 0 or lambda is equals to minus lambda bar, and this implies either lambda equal to 0 or purely imaginary. Okay. So, for a real skew symmetric matrix, eigenvalues are either 0 or purely imaginary. So, these are second property for skew symmetric matrix. Okay. So, okay. The first property is here the elements of the main diagonal of a skew symmetric matrix are 0, and therefore, its trace is also 0. This is very easy to show. You see that if a matrix is a skew symmetric matrix, then A that is diagonal element A11, A22, A33 and so on, it will be equal to minus of A because A transpose equal to minus of A for all I, and this implies A equal to 0 for all I. This means diagonal elements of a skew symmetric matrix are all 0, and hence the trace is also 0, because trace is nothing but sum of diagonal elements. The next property we have shown that each eigenvalue of a real symmetric matrix A is either 0 or purely imaginary. Now, if A is a real symmetric matrix, then determinant of A is always greater than or equal to 0. This is again easy to show, because we have shown that eigenvalues of skew symmetric matrix, real skew symmetric matrix, are either 0 or purely imaginary. Okay. If one of the eigenvalue is 0, so determinant will be 0, because determinant is nothing but product of eigenvalues. Okay. So A has eigenvalues like 0 plus minus alpha I plus minus beta I, like this, the eigenvalues of A, if A is a skew symmetric matrix. So, if 0 is one of the eigenvalue, then the product will be 0, that means determinant is 0. If 0 is not an eigenvalue, suppose eigenvalues are plus minus alpha I plus minus beta I types. So, if 0 is not the eigenvalue of a matrix, skew symmetric matrix A, then the eigenvalues are of the types plus minus alpha I plus minus beta I plus minus gamma I, or so on, and determinant of A will be nothing but product of eigenvalues. So, if you multiply these two, it will be alpha I minus alpha I, so product will be alpha square. Similarly, product of these will be beta square, product of these will be gamma square. So, product of eigenvalues will be something like this. So, we can say that determinant of A will be greater than or equal to 0, because complex roots always exist in pairs. Any real skew symmetric matrix of odd order has determinant 0, that we have already seen. Now, Hermitian matrix. A complex square matrix A is said to be Hermitian if it is equal to its own conjugate transpose, that is A conjugate transpose is equal to A. So, let us see this example. Suppose it is for the Hermitian matrix, we have seen that it is A conjugate transpose is equal to A. The first most property for this matrix is, you see that AII, which are diagonal elements, conjugate should be equals to AII for all I. So, this implies AII for all i's are real. So, the first property of Hermitian matrix is that the diagonal elements must be real. It is a complex matrix, but for Hermitian matrix all diagonal elements must be real. So, you take this example, suppose it is 1, it is 2 plus 3 iota, it is 2 minus 3 iota, and suppose 4. When you take the conjugate of this, conjugate is 1, conjugate of this is 2 minus 3 iota, conjugate of this 2 plus 3 iota, and 4. Now, when you take transpose of this, it is 1, 2 minus 3 iota, row will go to column, 2 plus 3 iota and 4. So, which is equal to A. So, we can say that this matrix is a Hermitian matrix. Now, the next property of Hermitian matrix is all eigenvalues of Hermitian matrix are real. The proof follows on the same lines as we did for symmetric matrix. You take Ax equal to lambda x, okay, the proof is same. You can see here we are having A bar transpose equal to A, okay. So, Ax equal to lambda x you can take here, x is not equal to 0, take bar both the sides, take transpose both the sides and replace A bar transpose by A. X bar transpose A is equal to lambda bar transpose, it is x bar transpose Ax equals to lambda bar x bar transpose x, x bar transpose it is lambda x and it is lambda bar x bar transpose x. So, this implies lambda minus lambda bar into x bar transpose x equal to 0, and since this is not equal to 0, so this implies lambda equal to lambda bar. So, hence all eigenvalues of Hermitian matrix are real. So, the properties are of Hermitian matrices, the diagonal element of Hermitian matrix are necessarily real. all eigenvalues of Hermitian matrix of order n are all real. Now, the inverse of invertible Hermitian matrix is also Hermitian. Okay. You can see the proof is very easy. You see here A conjugate transpose is equal to A because A is Hermitian. We have to show that if this matrix is invertible, if this matrix A is invertible, determinant of A is not equal to 0, then A inverse is also Hermitian. So, A inverse Hermitian means for A inverse also, for if B is A inverse, then B bar transpose is also equal to B. This we have to show. So, you can take B bar transpose. B bar transpose is A inverse whole bar and transpose, which is same as A bar inverse whole into transpose, which is same as A bar transpose whole inverse. This is by the properties of matrices. Okay. And A bar transpose is A because A is Hermitian. So, it is A inverse and this is nothing but B. So, we have shown that B is equal to B bar transpose, that means inverse of Hermitian matrix if A is invertible is also Hermitian. Now, the product of two Hermitian matrices A and B is Hermitian if and only if A B is equal to B A, and thus A raised to power n is Hermitian if A is Hermitian and n is a positive integer. So, let us try to prove this. The second proof is follows on this. So, product of two Hermitian matrices is Hermitian. This we have to show if and only if A B equal to B A. So, let us take A and B two Hermitian matrices. Okay. Two Hermitian matrices. That means A bar transpose equal to A and B bar transpose equal to B. So, we have to show that A into B is also Hermitian if A B equal to B A. So, let us take this whole transpose and try to show that if A B equal to B A, then this is equal to A B. So, this is equals to A bar B bar whole transpose, and this is equals to B bar transpose A bar transpose, and this is equals to B into A because A and B are Hermitian matrices and A B is equals to B A. So, this is equals to A B. So, we have shown that product of two Hermitian matrices is also Hermitian if A and B, if A B equal to B A. Similarly, we can show that B A whole bar is transpose is equals to B A. Same lines. Now the converse part. Now, let us suppose this is Hermitian, that is this is equal to this, and we have to show that A B equal to B A. Okay, the second part. So, to show this part, so this implies A bar B bar whole transpose is equals to A B, and this implies B bar transpose A bar transpose is equals to A B, and B bar transpose is B and this is A. So, it is equals to A B. So, we have shown that this is equal to this. So, hence we can show, if we substitute B equal to A, then A square, A square is always equal to A square. So, that means A square is also Hermitian if A is Hermitian. Okay. And similarly A cube, similarly A raised to power 4. So, this proof we can simply get. So, that means if A is Hermitian, then any positive power of A is also Hermitian. Now, for skew Hermitian matrix, a matrix with complex entries is called skew Hermitian if A conjugate transpose is equal to minus of A. So, what are the properties of the skew Hermitian matrices? You see here A bar transpose is equals to minus A. That means first of diagonal elements. So, this is equals to minus of AII for all I, and this means AII for all I are either 0 or purely imaginary. Okay. The first most point for skew Hermitian matrix, the first property. The second property is all eigenvalues of the skew Hermitian matrices are either 0 or purely imaginary. The proof we can easily obtain, okay, following the same as we did for a skew symmetric matrix. Okay. Next is if A is a skew Hermitian matrix, then iota A and minus iota A are Hermitian. So, this is easy to show. You see A is a skew Hermitian, that means this is equals to minus A. You take B1 is equals to iota A and B2 is equals to minus iota A. So, if you take B1 conjugate transpose, so it is minus iota whole conjugate transpose. So, it is iota conjugate and A conjugate whole transpose. So, conjugate of iota is minus iota and it is 8 bar transpose, and A bar transpose is minus A because A is a skew Hermitian, it is given to us. So, it is iota A, which is B, which is B1. So, we have shown that B1 is Hermitian matrix. So, similarly, we can proceed for B2. If we take B2 bar transpose, so it is minus iota A bar transpose. So, this is minus iota bar A bar transpose, minus iota bar is iota, and this is A bar transpose is minus of A because A is skew Hermitian. So, it is equals to minus of B2. So, it is equal to B2. So, we have shown that B2 is Hermitian matrix. So, if A is skew, A is Hermitian, A is skew Hermitian, then iota A and minus iota A are Hermitian matrices. So, here we have seen some of the important matrices like symmetric matrices, skew symmetric matrix, Hermitian matrix and skew Hermitian matrices, and we have seen some of the important properties of these special matrices. In the next lecture, we will see some more special matrices like orthogonal matrices, unitary matrices, etc., and their properties. So, thank you.